So we will just start today's session, continue from the wherever we left. Every processor should provide a place for storing the operands. So we will start discussing about the different addressing modes supported by in general any processor. So we have discussed the 5 addressing modes what are supported by the processor. So the first addressing mode is, as we learned, that it's an immediate addressing mode. So example we studied is, if I want to move any number 20 into any of the register, it becomes an immediate addressing mode. So the second addressing mode is called as register addressing mode. If registers are involved in the movement of data one place to other place, or if registers are part of the arithmetic or logical instructions, so then we can call as register addressing mode. Then after these two addressing modes, all other addressing modes, whatever we are discussed and going to discuss, are all memory related addressing modes. In the sense, one of the operand will be the memory operand. In the first two cases, there is no memories involved. The whole of this number 20 and the register encoding is a part of the single instruction. So memory, we are not referring it. In the second addressing mode also, here the register R0 and R1 are all encoded in the same instruction. So we don't require a memory operand also here. So from all the instructions which uses the addressing mode third onwards, they are memory related. So we discussed the first addressing mode is called as a direct addressing mode, also called as absolute addressing mode. Here in this type of addressing mode, we are referring a name of the memory location or address of the memory location in instruction. For example, LOC R2. So whenever I use any of the label name like this, we should understand that it is nothing but one memory address. Instead of location, I can also specify 2000. So hash means it's an immediate, it's a part of the instruction, it's a data. When I just give some label name or number without the hash, it means that memory address. So I'm bringing the contents of the location to R2. So I've also explained, we have discussed that whenever a repeated operation is to be performed multiple times, so direct addressing mode do not support adding the contents of list of numbers, because each time at the runtime I have to refer to the different address. For that, all the processor supports what is called as memory indirect addressing mode. So memory indirect addressing mode support the concept called as a pointers. So here the register normally holds an operand. In all these cases, register normally holds an operand here. But now for the first time, I'm using the register to hold address. The moment register holds an address, it is called as a pointer register. So registers in most of the processors are capable of holding either the data or an address. So in some Intel processors, there are specific registers that are HL, BC. So these registers are meant for holding the address and also data. For example, AX register is an Intel, which holds only the data. In most of the ARM processors, the registers R0 to R31, whatever available, we can use it for either holding the data or the address. It's only the responsibility of the programmer to keep in track that the registers use address or the data. So the example for this is, we know that whenever we use a register as a pointer, I have to use a bracket. The moment bracket is used around a register, you should keep in mind that R2 is a pointer now. R2 holds an address, not the data. So I can bring this data into R0. So the meaning is contents of memory location which is pointed by R2 is moved into R0. Then we also understood that if I want to access the arrays which are stored in the memory at different places, So I want to refer that arrays starting at a particular place. Then we can use what is called as indexed addressing mode. So indexed addressing mode is also used to access the different elements of a record. Indexed addressing mode. So in this case, we will be using a constant or a displacement as a part of the instruction. So for example, so as I told in the last class, R0 and then we use R1. This displacement we call as X in general X, it can be any number. We generally use what is called a signed number here. When I say signed number, that means the displacement can be towards the, it can be subtracting from the R0 or adding something to the R0 also. That means that if there is a record is there, you can access an element before the reference or after the reference also. So generally this constant will not be of 32 bits. So will be of a smaller size 8 bit. Since it's a smaller bit 8 bit, whenever we are performing an addition of 4 to the R0, generally sign extension of this 8 bit into 32 bit is done automatically by the processor and then added to the R0. So till this we have studied in the last class. Today we will just go through another 5 addressing modes which may not be useful in a normal simple programs, but which are useful when we develop programs which involve matrices, multidimensional arrays, and we perform a branching from one place to other place. All those cases can be handled by the following addressing modes. So one by one we will study them. So other is base indexed addressing mode. Based indexed addressing mode. So an example, we will study with an example. So what is an example for base indexed addressing mode? And we will write again the bracket here. But normally the bracket contains one register in the previous case. Now I am specifying the two registers in the bracket, R0, R1, and then R2. Here, the effective address, the place you are referring in the memory, we call as an effective address, is nothing but what? Contents of R0, you are adding it, plus you are adding what is called as R1. So that means that adding R0 and R1, you get one address. That is an address you are interested to access it. In that address, you are able to refer the data and then you take the data. So summarizing, I can tell like that. When I say add R0, R1 bracket R2, the meaning is contents of memory location whose address is the preparation of R0 plus R1 will be accessed and that data will be taken for addition. So such addition of two registers to prepare one address so will be used in a base indexed addressing mode. What is the advantage of this type of addressing mode? In a two-dimensional arrays, one can be pointing to the row, the other pointer can be pointing to the column. So whenever we are accessing a two-dimensional arrays, this type of base indexed addressing mode can be used. The next one, so base indexed with displacement, base indexed with displacement. So it is similar to the previous one. Only thing is, in this case, you can also add a constant along with the two registers. So R0, R1, some 10, I can add it, then R2. Here, the actual address of the memory is nothing but what? It is nothing but effective address in this case is the constant 10 plus the contents of R0 and the R1. So it is used when a multidimensional arrays or matrices are located in a particular place in the memory. From their reference, I should be able to start it. The eighth one. So eighth one is a very typical addressing mode, which is little difficult to comprehend like the previous one. Let's understand what is the meaning and why it is required. It is called as the relative addressing mode. Relative addressing mode. Now, so before we understand this addressing mode, we will understand a small requirement of this addressing mode first by writing a small program in a relative addressing mode. Now, let's say I have a small program requirement is there. The program requirement is now the program requirement is I have a program. So it is starting some add instruction, some logic, and then instructions continues like this. After that, I want to take a decision. If branch if it is greater than 0, branch, if it is greater than or equal to 0, I want to go to a particular place. That is, I want to repeat that instruction loop. I have written it. So this is my requirement. Now, I want to execute a program. After some time, I'll be checking for a particular condition. If it is answer is previous answer is greater than 0, I want to go to the loop. Now, in such cases, how do we encode? How do we encode this instruction? Now I want to convert this instruction into a machine language instruction. We know that every instruction requires, let's say, 32 bits. I want to convert this instruction to machine language. One is opcode. So you are indicating that means that this is a branch instruction. Next, I have to encode in this instruction one information, that means that the address of the place where I supposed to jump, loop. If I include the full address of the memory location where the loop is associated, it is a 32 bits. That means that the instruction size will exceed the 32 bits because I cannot accommodate the complete 32 bit address here. That is why what they do is many times branch instructions, the distance between the branch instruction and the label where you're supposed to branch will be very less value, maybe 1K, 2K or less than 64K. You don't require 32 bits to represent. So it is required to represent the displacement with reference to this instruction, how far it will be useful. In the sense, if I am able to refer this loop in the complete memory location, that means that, see, if this is the memory location, if this is starting from 0, let's say it goes up to 1 GB, 1 GB minus 1. So if you are referring to a label loop, that means that the address of this is 32 bits, because why? I am referring this with reference to what? From 0 to 1 GB. But instead of referring this one, if I refer this address called loop from a place, that is, where is a place now? Let's say I'm executing at this place now at this moment of time. That means that my program is there, add instruction. Here is a branch instruction is available. Now, if I want to find out how far is a loop from this place, then instead of representing the complete loop inside the instruction, if I just indicate the displacement, how far is a label where I supposed to branch into the instruction, it takes very less amount of space. So that is why almost all the processors provide a facility of indicating the offset from the reference where you are executing it. From that place, how far is your label? Then the number of bits what is required to encode that offset will be very less, instead of absolutely specifying the actual address from 0 to 1 GB. So this concept is used. Now, what is the requirement here? I should know that where is the reference now, that is from which point I have to compute my offset. So always we know that there is a special register called as program counter is present in almost all the processors. Program counter indicates which is the instruction which you are executing currently, and always it points to the next instruction to be executed. When you are executing the branch instruction, it always points to what? The program counter point to the next instruction. So that means that program counter always points to the next instruction to be executed. So if I know the program counter value, I can always find out with reference to program counter, I can specify the label. So this method of using the program counter contents and the label where you want to branch is the concept called as relative addressing. So let's go back to the now relative addressing. Now we have understood that a relative addressing is nothing but an addressing mode where we specify in the instruction an offset value or displacement value with reference to program counter. So that's why the relative addressing mode, the instructions what we write is, so the effective address of in the relative addressing mode is nothing but program counter value plus x. X is what? Displacement will be loaded into the program counter. Now, so when is this instruction used? When we use for branch instructions. So whenever branch instructions are used, so the effective address is calculated by adding the contents of program counter plus x. So that means that when I say program counter plus x, it is nothing but the difference between the program counter and the value of the label. So I can write this as target address. Target address means the label. The target address is a label plus minus current value of PC. So this value is nothing but this is referred to this one. So the x can be minus value also, x can be plus value also. Effectively, the contents of PC will be added some value or will be decremented. If you are branching to the back, that means current instruction, from the current instruction you're going back means x is negative value. If you're branching ahead of the current instruction, x value is positive. So effectively, the contents of PC will be added to some constant called x, which is a signed number, and the new value of PC will be generated. That is a place where you're branching. Encoding this type of information inside an instructions is that type of addressing mode is called as relative addressing mode. So where is the relative addressing mode used? Relative addressing mode is used whenever we write a branch type of instruction. So in case of branch instruction, instead of other registers, the PC is used. Already this concept, we are using the registers in other places, but here specifically PC is used for this purpose. Now let's go to the other two addressing modes. Other two addressing modes are extensively used whenever you are accessing the bulk of data. I want to access 100 words. I want to write 100 words into the memory. Then you need not require to increment the pointer. Automatically the instruction or addressing mode supports auto increment. So that is the meaning of the 9th and the 10th instructions. It's called as auto increment addressing mode. So what does it mean that? So we will take an example and understand. And let's say R2 bracket, the moments R2 is a pointer. We use a plus symbol after that and then R0. So everything is same. Only thing is I've introduced a plus symbol. So what is the meaning of a plus symbol? So here the contents of the memory location are referred by R2. So we say effective address is the R2. In this case, effective address is what? R2. So we are using the contents of the memory location. We are referring the contents of a memory location which is referred by R2, and then we access the data. So we will take the data and add to the R0. After performing this operation, then what will happen? The second step is the R2 is incremented. So how much it's incremented? If I'm referring the instruction for a word, it's incremented by 4. If I'm accessing a byte, it will be incremented by 1. If I'm accessing a word, half word, it will be incremented by 2. So the processors are capable enough to understand the instruction, by the instruction, whether it's incremented by 1, 2, or 4. That is a word length. So what is the meaning of this instruction? That means that add the contents of memory location pointed by R2 to the R0, store the answer into the R0. After performing this operation, increment the R2 automatically. That means that in the last class, after adding, we were physically doing the increment. So generally what we do is we perform add, then we perform like this, and then we were adding add 4 to R2. That means that we are physically doing it. Instead of doing these two, a single instruction is enough. So wherever you are incrementing the pointer after the operation, you can go for this type of instruction. So it's very useful when we access the bulk of data, bring lots of data from memory to the inside the processor, or you are moving set of register contents from the processor to the memory. We use this one. The last addressing mode is called as auto decrement. So auto decrement mode. So this is useful to implement the stacks. So let us understand by an example. Auto decrement mode. So I'll be using an instruction here. So in this case, I am referring again a register as a pointer. I'll be using as a pointer, but instead of using a plus, I'll prefix the minus here and then R0. As the name says, I'm using this for a stack implementation. Stack grows in the process usually from higher address to lower address. So what is this instruction will do it? So it will do two steps. The first step is it is going to decrement the value of R. In this case, R2 by 4, by 2, or by 1, depends upon the word, the half a word or byte you are accessing it, and then you are accessing the data. So after decrementing, then you are accessing the data. So what is that we are accessing here? The accessing is effective address. In this case is nothing but so R2. So we are referring it. So in this case, what we are doing is we are decrementing the pointer by 4, and then we are using the new value of the R2 to access the memory location. So This is another way of using the instructions whenever pointers has to be incremented and decremented continuously. So these are the 10 addressing modes supported by most of the process. This does not mean that every process supports all the 10. For example, so if you take a small microcontrollers or small the processors, which may not support all the 10, so which may support 6 or 7. So that means that it is a comprehensive list of all the 10 addressing modes supported by most of the processor. Some processors support 8, some processors support 9, some processors support all the 10. So this is the addressing modes. Almost all the addressing modes used in the current the process in the market are being listed into this one. Now, so now we will go to the once we had understood the addressing modes. So it is required for us to now what else we require to know to write efficient addressing ratio efficient ALP program. To write ALP programs, basically, we require to know three things. Number one is I should know all the instructions which are available for the process, that particular process. Next is I should know what all the addressing modes supported so that I can able to use effectively the operands of the data inside and into the memory also. The another is what is called as very important is called as a flags. So we call it a conditional flags. Now we will study the third concept which is required to write efficient assembly language programs. So conditional codes or conditional flags. So what are the flags? When I perform any operation, when I perform some add instruction, I'll perform. So add R0, R1, R2, I'll perform. Then after that, I want to branch if it is greater than 0 or equal to 0, some other label I want to branch it. That means that any time you execute any instruction, after that, there is a very good chance that you may use a branch instruction to implement if and else. You want to implement a for loops, while loops, you require a branching is required. That means that anytime processor performs an arithmetical logic instructions in general, it is required to set certain information in the processor so that this instruction can look at that information and take a decision. That means that there are certain places you have to set up. There are you have to set up inside the processor. So these places should contain certain value. What is that value? Now add instruction is performed. I have to set certain information in these places. What is the size of these information? It is to be just yes or no. That for example, if I perform an add instruction, if my answer is 0 or not, if it's 0, you make it 1, otherwise 0. So that means that, so that type of 1-bit flip-flop, which is used to indicate certain information about what happened in the current instruction, is called as a flag. So flag is a 1-bit flip-flop used to represent certain indication whenever the instruction is executed. So flag, this is called as a 0 flag is available. So 0 flag, whenever it's set 1, that means that answer of the current instruction is 0, or we can say that answer of the previous instruction which is executed has produced a result of 0. So 1 means 0, 0 means answer is not 0. Similarly, there's another flag as negative flag. So this flag is also 1 or 0. Whenever this flag is 1, that means that the answer produced by the previous instruction is negative. So how does a negative flag will be set? The last bit of the answer will be used in sign numbers. The last bit is used to indicate a sign. So the last bit, if it is a 1, it's a 2's complement number. That means that it's a negative number. If the last bit is 0, it's a positive number. That's how negative flag will be used. Similarly, there is another flag called as a carry flag. So what does a carry flag indicate? Whenever you add the two numbers, the last bit generates the carry. If it's a 32-bit number, the D0 to D31 are the bit numbers. D31 bit will produce the carry. So this is very useful whenever you add multi-word numbers. I'm adding a 64-bit number. How do I add it? I will add first 32-bit numbers. Then I take the carry what is generated by the first 32-bit number, and I'll go to the another 32-bit addition with the help of the carry generated from the previous 32-bit numbers. So like this, carry flag is also has got a significant usefulness when we develop assembly language programs. So whenever this bit is 1, that means that carry is generated. 0 means carry is not generated. One more flag, overflow flag, which is a very important whenever you do a signed operation. Overflow flag is used only in case of signed operations. Whenever you perform a signed operation, there is a range is there. That minus maximum value to plus maximum value. If we take, for example, 8-bit number. So what is the range? The last bit is used for what? Sign. So how many bits are left now? 7 bits are left for a representation. So if there's an 8-bit number, for understanding sake, If this is a sign bit, so sign bit can be 1 or 0. The remaining will be what is called as the magnitude. So that means that I can represent from minus 128 to plus 127. I can able to represent. If I am going to add two numbers, let's say plus 120, I am adding it with another plus 120. Then my answer is what? 240, which cannot be held, which cannot be accumulated, or which cannot be represented in an 8-bit number, because 8-bit number maximum is what? Minus 128 or plus 127. So whenever you add two signed numbers, there are chances that answer can exceed the range what you can able to store in a given 8-bit number. So such cases, overflow flag is used. Always remember that overflow flag is different from a carry flag. Carry flag is meaning is there in case of unsigned numbers, whereas overflow flag has a meaning in a signed numbers. So it can be 1 means overflow flag, 0 is 0 flag. Most of the time there is no single bit flip flop will be there, because we know that in a processor everything is nothing but a word, nothing but like a word. So that means that generally these 4 bits are put into a one register and made a part of it, maybe. So they may accommodate the first 4 the bits of this register, and the total register will be called as status register or flag register in most of the processor. So that means that what is a flag register? A flag register is a register which can be of 32 bits or 16 bit, depends on the processor word length, and few of the bits in that register are used to represent the flags. So whenever we are referring the flags, we refer this register. So this is the way how the flags are implemented inside the processor. There are certain instructions for that. For example, in ARM, when we write an instruction, I can write yes, I can write it, or I can write only add. That means that if I request the processor to set the flags, correct now, update the flags status, then only status flags will be updated. If I don't suffix yes, if I just use add, the flags will not be updated. So this facility is provided in most of the latest processors, so that flags to be affected or not affected, it's the programmer decision. Why they have supported this one? Because in a pipelining, it's very important when you want to implement the pipelining and the parallel processing. Sometimes it's not required to affect the flags. So in such situations, it is a programmer's decision to either to use add s or add. So this is about the conditional flags. Now, now let's go to the next concept about the assembly language programs. Now we have understood the instructions, basic instructions, what we have used. We understood also addressing modes. We also understood the 4 flags which are generally present inside of the any processor. Now, it's a time for us now to write some programs which involves input-output devices inside the processor. And also, before writing the program, let's understand one basic concept. So, what is the difference between assembler directives and assembler instructions? So, sometimes when we write a program, like this, org, so 00000. I write my instructions here, all the add or whatever required. Then I say org, so 2000, I'll write it hexadecimal. Then all my reserve my data here. The data can be what? It can be location, defined word, some space I can give it, or string, defined byte. I can store some character strings. I can able to do it. And before that, I can give a name for that. So for example, some EQU, and so let's say 1000, I can able to like this. These are the style of writing assembly programs. What all I have included? See, if you look at that, I have included some instructions. So these are the instructions which are converted into machine language. But along with these instructions, I also represented the data, because data is also part of the instruction. Again, these instructions also encoded into the memory. So both instructions and the data will go into what is called as memory. It will convert into object code and it will be sitting in the memory when the program is loaded. But what happens? What is this instruction? So what is this instruction and what is these instructions? So, and also at the end, we will have, when everything is over, we also write end. So what is the meaning of this one? So whenever we write any ALP program, basically ALP program comprises of 2 things. One is instructions to processor, other is called as instructions to assembler. So assembler is a software which is used to convert your assembly language program to machine language program. So when assembler has to work properly, generally assembler works in 2 passes. That means that First is go through all the instructions wherever the names, the labels are used. For example, some, so wherever the labels are used, like a loop and all those labels, it recorded the addresses associated with the labels. So it maintains what is called symbol table. Again, after going through the one pass, it may not able to identify find out the address for every label, because sometimes you are referring to a label for you're jumping to a location which is ahead of the current instruction. So ahead of the current instruction means you do not know at this moment of time what is an address associated with that label. So that's why assembler goes through one more time. That is two passes. We call it assemblers as two pass assemblers. So when assemblers go through your program two times, it is able to understand all the addresses associated with the labels and the jump locations, everything. Then it is able to convert into a machine language program. So when assembler performs this going through the program, it requires certain instructions. What are the instructions? For example, simple instruction org. Org means start loading this program from the memory location called 1000. Now, when I say org 2000, code the data. That means put the data in the memory at the address called 2000. Then equals. Equal means like a what is called as in the C language, what is called hash defined statement. That means that whenever 1000 is referred in the program, so it is equivalent to what sum. That means that instead of physically referring 1000 in the program, I can refer by name called sum. It is nothing but naming a constant. So EQ is what? Naming a constant. So that means that it simplifies program writing in a machine learning language. So these type of instructions to assemble EQ, ORG, and end is a logical end of a program are called as assembler directives. They are called as popularly called as assembler directives. So what are the assembler directives? Assembler directives are what? Instructions to assembler. So assembler directives are instruction to assembler. So any assembly language program always comprises of two things. One is instruction to processor, which is nothing but supplied by the processor manufacturer, which are converted to machine language. Other instructions are nothing but it just instructs assembler how you have to convert the program into machine language. It's an instruction to assembler. So assembler directives are not converted to machine language, whereas instructions are converted to machine language. So I'm audible?
Yes, sir, audible.
Now we'll go through a few programs of assembly language. So where we learn how assembly language supports input-output devices. Now let's take now the requirement like this. So now the requirement is I have to interface, let's say a keyboard and a printer to processor, and write ALP program or machine level language program to read from keyboard, and store in memory, and also print on the printer, So let's say this is my requirement. So I have to write an assembly language program where I supposed to interface the two devices. Let's understand how the interfacing will happen. Now let's say this is the processor, and the processor is also connected to the memory. So memory is available. Till now, the processor was connecting to only memory. So till now, we have understood that how processor address, data, and the control buses are used to access the memory locations, because we have a move instructions available, we have a load and store instructions available. Through that, I can able to access them. So inside the processor, we understood that there are so many registers are available. Now along that, now I have introduced one more device called as an input device, and the name of the input device in this particular case, it's a keyboard. And I have one output device I have taken. In this case, it's a printer. The printer. Now again, input device, and it's an output device. Printers, because it gives the status also. So I've written a bidirectional. Now this is the scenario. Now let's understand that when I want to read from a keyboard, processor can read the keyboard like that. input device. When the processor wants to send something to the printer, can the processor can send directly to the printer like that? First of all, we have to answer the following question. What are the first questions? What is an address of these devices, input output devices? Because we know that memory is connected to the processor. The address bus of the memory helps the processor to identify one of the processor locations, one of the memory locations, and access the memory. We know that using a move instructions, we can able to access any of the memory location using direct addressing, indirect addressing. But how does an input output devices can be addressed? So there are two techniques are there which we popularly provided by most of the process. One is called as IO mapped IO. This is a technique where the addressing of IO device is taken care. Other is called as memory mapped IO. These are the two popular techniques used by almost all the processors which is currently available in the market. So Intel processor, they followed what is called IO mapped IO. That means that there is a provides separate instruction called in and out instructions are provided to access what is called as the input output devices. So separate address space is there. So whenever in and out instructions are used, they may use the existing 32 address lines which are used for memory. Among that 16 address lines, they may use it to generate an address. So the processor, whenever in and out instructions executed, processor generate a special pin on the processor is there called IO bar, IO M bar. There's a pin called IO M bar is there. So these pins identifies whether the address which is coming out of the processor is going to the input output devices or to the memory. So same address lines are used, but not all the address lines carries the address. So if I use instruction called move, it's understood that it is address is referring to what? The memory. When I use in and out instruction, it refers to what? It's input output devices. How does the devices or the memory knows? By using a line called IO bar M bar. This is one technique which is used by the Intel process. But apart from the Intel, most of the current process, including the ARM, they support what's called memory mapped IO. What is the meaning of a memory mapped IO? In memory mapped IO, you do not have a separate instructions for reading input output devices are there. But the total address space, whatever available, let's say 4 GB is the space available for Intel 386, 486 processor. That means that they use one maximum portion of this address. Let's say they use 3.5 GB. They may use for memory. So remaining 0.5 GB, they may use for IOs. So they will partition the total address into some portions. So these are the addresses are meant for what? The memory. The remaining addresses it's used for IO. So this partition can be done by the designer. When they design the motherboard, he can take a decision where all the memory is located, what all the addresses I can give for the input output devices. So that means that you're treating input and output device as a memory. The memory mapped IO technique is what? Input and output devices are treated as memory locations, That means that if you're trying to access any of the address in this space, that means that when you use a move instruction to access particular address, that means that you are reading or writing to what? The input output devices, not the memory. So you may ask the question, so why do we require a memory address for a keyboard or printer? We know that keyboard means it's a place where I can read some data. So inside the keyboard, there should be a buffer or there should be a register like a 8-bit which holds the key. That is why an address is required. Similarly, printer. When I send something, a print also should have some register which holds the data which has been sent by the printer. So that is why it requires an address for the printer also. So most of the times we use a memory mapped IO these days. Now, now I have addressed the one of the called how do we address the IO devices. Second question I have to address is what? The speed synchronization. The speed synchronization is required. The processors are at work at gigahertz speed, whereas your input output devices it works at a megahertz, kilohertz, even less than that. So that means that the speed at which your instructions are executed are very high compared to the speed at which your input output devices will work. So when I write something into the printer, the rate at which I write in the printer may not understand the data. It will lose the data. Similarly, so I should be able to read the keyboard only when the keyboard data is there. In the sense, since the processor works at very high speed, we should be able to synchronize between the keyboard and the printer or input output devices with the processor. If the synchronization is not done, then what will happen is you lose the data or the devices will not receive the proper data. So only the junk data you will be getting or the junk information will be received by the printer. Many times whenever we interface input-output devices, if some junk characters are coming, immediately you should think that what is the problem? Synchronization is the problem. Now, to achieve the synchronization, two techniques are generally used in the industry. One is called as program controlled IO. Program controlled IO. The other is called as interrupt driven IO. Interrupt driven IO. So in a program controlled IO, it is a responsibility of the programmer by using a proper instruction to keep check whether the device is ready so that I can send the data. So I should keep checking the keyboard. Do I have the data? Then only I will read it. So it is like a blocking code. That means the program is executed continuously in loop to access the input-output devices. So generally what will happen is it is like a blocking code. That means in the sense the processor is completely engaged in case of a program controlled IO. Now we write one code for a program controlled IO. Then we will come back to interrupt driven IO. Now I will write the code now for doing the job whatever been asked here. Now what is the job here? Now I supposed to read from a keyboard. Every keyboard provides what is called as one register inside, that is called as a buffer register, which contains the keyboard data. I'll assume it's now the name of that register is data in. Data in is the name of the register which holds the key code whatever you pressed on the keyboard. Now it also contains one flag bit or one bit which is called the status of the keyboard, SIN. So SIN says that whenever SIN is 1, the bit is 1, that means that whatever the key user has pressed the key, the code is present in the data in. When should the processor read the keyboard? Only when the data is available, I should be able to read it. Otherwise, if some other times I will read it, I'll get some 00. That means that it's a junk code. So reading at appropriate time from the keyboard is very essential. But when to read, how do we know that? That is why a flag is required. So that means that you are achieving the synchronization between the high-speed processor and the keyboard by providing two important information inside the devices. One is called as a buffer register, other is called as a flag. So buffer register and the flag is a concept used to synchronize between the processor and the input-output devices. Now I'll start writing the program. Similarly, I'll also write for the printer. So printer also will have one register, a buffer register, which holds the data sent by the PC. It's called as data out, I'll call as. Similarly, the flag which is used for synchronization called as status flag out, status out. So this status out indicates that whenever the status out, the flag is set, that means that printer is ready to receive the next character. So now I have the two flags which helps me when to read and when to send the data to the printer. So now we will write a small program to implement this logic. Now, so I will check what is the data present inside the bit called the SIN bit. So generally we cannot read one bit at a time in any of the process. As I said in the previous class, the flags are part of a status register. Similarly, the flags what is present inside the keyboard also will be part of what is called as a status register. There is a status register present inside the keyboard. The flag, whatever the SIN, will be part of the status register. So when I want to read SIN, I have to read the status register. So now what we'll do is I want to test a particular bit in the status register. We will assume the bit number 3 is associated with the SIN flag. So now whenever I read the status register, I'm interested to look at what? The third bit, which represents the status in. So if the bit is set, the keyboard has got character. So how do we test? There is an instruction called as test bit is available. So test instruction. So test bit is nothing but an instruction provided in some of the process which tests a particular bit of a one word register. So now what is the name of the register? Now let's say status register name is called as in status register. In status is nothing but name of the status register of a keyboard. Now which bit I am testing? The bit number 3 I am testing it. So this instruction always affect the result. So test bit is nothing but an AND instruction. So whenever the bit 3 is 1, that means the total answer becomes what? It will be non-zero. By chance, if the bit 3 is 0, the total answer becomes 0. That means that this instruction will be set what is called as 0 flag. So when does a 0 flag will be set? If the bit number 3 is 0, the zero flag will be what? It will be set 1. If by chance the bit number 3, that is which represent SIN, is 1, that means zero flag is equal to what? It is equal to 0. So that means that is the meaning of a test bit. So test bit instruction will set the zero flag either 1 or 0. So after executing that, I'll check the condition. I'll write a branch instruction. If branch equal to 0, that means the zero flag is set. Branch equal to 0 means what? Zero flag is set. Still, I have not received the character. I have to go back and keep executing the same instruction. I'll do the read. So this is the type of what is called a synchronization. So these type of writing instruction in a loop continuously checking for a particular flag is called as program controlled IO. What is the disadvantage of this in this type of program? That means that program is continuously, processor is continuously in the loop. Processor cannot do any other work. But you can achieve the synchronization. The junk data is not available to the processor. The proper data is available to the processor. So this type of synchronizing high speed and low speed devices can be used with the help of this type of program. So what are the concepts we have used? We have used a concept called as a data buffer. We use a concept called as a status flag, status register in a particular bit in the status register indicate the status of the keyboard. And then we use instruction called test bit and the branch based on that. Now, once the branch is not equal to 0, I'll come to the next instruction. What is the next instruction? That means the data I can read now. So how do we read? We can know that we can just use move byte instruction. Assume that so the name of the register, what is present inside the keyboard is data in, which is nothing but a memory address associated in the memory map 4 GB of the total address space. I am reading into a memory location. Let's say I have set up a pointer in the R0 register. I'll write like that. That means that the data present in the keyboard, I am reading into a memory location which is pointed by R0, where I can initialize R0 to some location in the memory. So before the program starts, we can write one instruction, move some location in the memory. So I can call as a location to R0. That means that setting up a pointer is being set up. Now, similarly, after doing that, I can write to the printer now. How do you write to the printer? First, check whether the previous data, whatever sent to the printer, is completed. That the printer has completed, printer has assimilated the previous data, what has been sent to the printer, has finished printing. How do you test it? Again, test a bit. So we'll assume that again the SOut, the bit of the printer, is being part of the status register which is present inside the printer. So I will check, assume that bit number 3 of the status register of the printer. So I will call the name of the status register out status. Now, if same concept, we'll use it, branch. If it is equal to 0, that means the still printer has not finished the job. You go back, echo. So keep waiting for that. Keep waiting for that. Now, if it is finished printing, means it will come back to the next instruction. So what is the next instruction it is supposed to do? I will write the data which is stored in the memory location into the printer. So where is the data is available? It's available in the memory location pointed by R0, and I'll store to the printer. Now data out. Now it goes to the printer. Now after that, if you want to continue the program, I want to read till I press an enter key in the keyboard, you can continue writing some more instructions. So what are the instructions I can write it? Some more instruction. I can compare if the person has pressed what is called as carriage return. Carriage return is what is called as enter key. So carriage return. Compare is an instruction which is used to compare any two numbers. So here what I'm comparing what is there in the what is the number stored in the memory pointed by R0 is equal to carriage return. If it's not carriage return, I'll go back to the reading same program from the beginning. So if it is a correct character, it's not a carriage return, I have to increment the pointer to the next. I will use auto increment now. I'll say plus now. So what will happen automatically? The pointer will be incremented now. So this is a concept where we can use it. Now I'll incremented the pointer. So I've just incremented the pointer here now. So it is nothing but I'm using here R0 plus I'm using here now. So now if the branch not equal to 0, I'll go back to the read program. Where does the read program goes? It will go back to this place. So this is how synchronization between the input-output devices and to the processor is done. So a lot of concepts there here. What is an advantage of this method? We are achieving the synchronization. Number one, there is no junk data reading. There is no junk data printing here. That is avoided. But what is the disadvantage here? That means that processor is completely engaged in the read and write loops. So processor cannot do any other job. Even though there is no requirement, processor is engaged. How do you avoid it? It can be avoided using what is called interrupt-driven I/O. In the interrupt-driven I/O, what we do is the program is what you are executing is different, and the program which is written for servicing the keyboard and servicing the printers are different. So we call as what is called three programs will exist. One is called as a main program. Other two programs called as interrupt service routines. We call as an ISR. That means that always you will be there in the main program whenever the keyboard generates an interrupt. So in interrupt driven IO, the devices should have the capability to generate an interrupt. Interrupt is a request to the processor to stop the execution of the current program and branch or call the interrupt service routine. So whenever the keyboard and the printers are capable of generating an interrupt, you can always go for interrupt-driven I/O. So interrupt will be generated whenever the keyboard receives the data. Then the main program will be stopped for a moment. The processor will jump to the interrupt service routine, which serves the keyboard reading and then finishes and come back. That means that you are always focusing on the main program. Only when the request comes either from the keyboard or from the printer, then you stop the program, go to the ISRs, finish the job and come back. So this is the current trend. This is where whenever we develop the programs, it's always better to write interrupt-driven I/O rather than a program-controlled I/O. So now, we will go to another concept now. How the stack is implemented in the process. So now we have understood that how IOs are supported at the machine level language and how we are able to write the programs to access the IO devices. Now let's go to the stack. Now, stack requirement is very much is there. If somebody asks in the low level language, machine level language, why stack is required? Number one, whenever we call the subroutines or nested subroutines, the stack is a place where I can store the return addresses. Whenever I call a subroutine, I want to pass the parameters, that is the data, to the subroutine. So one of the method to pass the parameter passing is what? Is through the stack. So both we call as a pass by reference and pass by value can be implemented using a stack. So stack is a common data structure which is used to create some space inside the main memory. So where is the stack is provided? If somebody asks a question, where is the stack is inside a processor? Is it inside the processor or outside the processor? So there are certain processors are available where there is a what is called as one register is available called link register. Only one level of nesting you can achieve. So that can be, you can call as one word stack, but it's a limited usage. But if you want the stack which can be used for storing the local variables, passing the parameters, everything, so that stack will be popularly called by name as process stack. So what stacks you used in the high level language programs is different. What I'm talking is different now. So what is the process stack? So process stack is nothing but a part of the memory which is not present inside the processor, but which will be present inside the main memory. So if this is the memory, so you have, this is the place where you have the programs, you have the data, ISRs, everything will be stored in this place. There is some place in the memory where you should use for stack. Now, so whenever you use a part of the memory as a stack, then the following questions comes into picture. Stack works on the principle of last in, first out. We know that. Now, whenever the stack concept is implemented, you require one special register will be required. We'll always specify where is the top of the stack. So that is why processors support a register called stack pointer is available. Stack pointer always point to the top of the stack. Now, how does the stack grows? Most of the processors implement a stack growing from a higher address to the lower address. Higher address to lower address is used. That means that so processors support the stack, and the stack is nothing but a part of the memory, and they grow from higher address to the lower address. There's a special register is available called a stack pointer, which is always point to the top of the stack. Now, so if there's a special instructions called push and pop is not available, we can implement the stack by the machine language instructions by writing one or two instructions. We will see that. Let's say push instruction is not available. How do you implement a stack? There are two operations are there inside for the stack usage. One is a push operations. Let's say now we have a stack. Assume that stack starts at the location called 2000 and it 500 words has been allocated for it, totally 500. So 1500 is the another address. This is the place where the stack is available. Now let's say this is the current top of the stack. Now, so if I want to now add anything to the stack, so what should I do it? So nothing but there is a register called stack pointer is there. I should be able to move the stack pointer either by adding 4 or by subtracting 4. Since the stack grows from higher address to lower address, if I want to put any data into the stack, I should be able to decrement the stack pointer and then you should be supposed to add it. Because why? Stack grows from higher address to lower address. Let's say at this moment stack is available here. Now what you have to do, when I say stack pointer is pointing here, means that this is the top of the stack. Now I want to put something into this one. So what should I do? I have to make the stack pointer point to the one word which is below that, because stack is growing from higher to lower address. Now I have to decrement the existing value of a SP by the 4. So I will write instruction called subtract hash 4 by stack point. I'll reduce. Now I'll push it. What is the data? Let's say I have a data which is available in a memory location called new item. So I'll take the data from the memory location. I'll put into the memory location pointed by the stack pointer, because stack pointer is a pointer now. So that's why I have to put a bracket. So this instruction is called as a push instruction. Sometimes some processor provide a single push instruction. If you just use a push instruction, both these operations will be done by the processor by itself. It automatically decrements, it automatically pushes the data into the stack top. If it's not available, you have to write instruction like this. Similarly, pop instruction. So pop instruction is nothing but what? I am just removing the data from the top of the stack and make the stack pointer increment, because why? Stack grows from higher to lower address. So I have to add 4 for this. It's the opposite of that. So what I have to do in case of pop operation, first take the data from the stack, from the top of the stack. So wherever stack point is pointing, that is the top of the stack. Take the data. Let's say I'll copy it to some memory location called item. Then after that, you have to adjust the stack pointer. So how much you have to adjust? You have to add 4 to the stack pointer. So this is called as a pop instruction. Again, if the pop instruction is automatically present in the process, it will do both of these instructions simultaneously. If it's not there, you would implement by these type of instructions. So you can add some what is called as checking to the beginning of this program. If you are pushing the data, just check whether the complete stack has been full. If there are 500 words of that, check for 500. So stack pointer, if the stack pointer has reached 1500. If stack pointer reached it, you can give an error called stack full. You can add to this here. Similarly here also, when the stack is completely empty, you can check a compare instruction, find out the value of the stack pointer, because you know as a programmer where is the stack is beginning and ending. This is the one thing difference between a high level language and a low level language. In a low level language, like say machine level language, it is the responsibility of the programmer to know where his stack is located in the memory, what is the size of the stack. Don't think that anything I can push, it will go into the memory. No. If you start pushing more than what has been reserved, then what will happen? The stack will write into the data and to your instructions. So as a low level language programmer, you should know where is the stack beginning, till what I can able to make the stack grow. Let's say 2000 to 1500, 500 words are there. So before popping or before pushing, I should check the stack pointer to see that whether stack is overflowed or stack is empty, and then I will supposed to work on it. So these two checkings you can able to add in the beginning of your program. This is how stack is being supported at the low level. But always make sure that every processor provide a stack pointer. Sometimes the general purpose register called as R13, R14 can be used as a stack pointer register. So it is the responsibility of the programmer to know that which register acting as a stack pointer. Don't disturb that register unless other than stack purposes. In some process, there's a special dedicated register called stack pointer is there. I can use that as a stack pointer. I need not. I don't use the stack pointer for general purpose storage. So these are the concepts related to the stack. Now let's understand another concept called as subroutine. What is the support provided by assembly language for the subroutines? Now, so whenever I write a subroutine in the program, the first thing I should know that the subroutine is also located in the memory. The main program is also located in the memory. So this is my main program. This is my main program. Let's say this is my subroutine. So I should know where is my subroutine is located. Let's say my subroutine is located at an address called 1000. Let's say its address called 1000 is located. Where is my program? Let's say my program is available at a memory location called 200. Now, so almost all the processors provide an instructions which makes the main program jump from the place to the subroutine. It can call. What is that instruction? It is popularly called as a call instruction. Call is an instruction supported by most of the processor to branch from one place to the other place. So let's say the name of this subroutine is called as SUB subroutine. So I'll call as what? Call SUB, or I can write call 1000. So the moment I call, I am branching from this place to this place. So my program execution starts here. Now, whenever we branch, we have to do two things. Number one, when you are executing the call instruction, the program counter is already pointing to the next instruction to be executed. That means that, so assuming that every instruction take one word of 32 bits, the next instruction is there in 204. So what is the value of the current value of the program counter? Is 204. When you are executing the call instruction, the program counter is already pointing the next instruction to be executed. Whatever may be the next instruction. So the address of that instruction is what? 204. That is available in the PC. If you branch from this place to this place, the program counter will be loaded with what? The program counter will be loaded with 1000, because program counter is always contains the address which indicates which is the next instruction to be executed. It contains 1000. So that means that when I finish this instruction, when I want to come back, I lost the contents of the program counter. That is why we have to store the contents of the program counter. For this, most of the latest generation processor provide what is called link register. So what is a link register, LR? Link register is nothing but a register which holds the current value of the program counter before you are going to the subroutine. So 204 is copied. It will be maintained here. Now, so it goes to here. Program counter is loaded with a new value. You complete all your instructions in the subroutine. Then there's a last special instruction is provided by the processor. That instruction is called return, RET instruction. So what is the meaning of RET instruction? Whenever the return is executed, automatically the contents of the link register will be copied into the processor. So on return, so what will happen? So while calling, you are copied from PC to the LR. So similarly, on return, when you execute a return instruction, the contents of LR. So what is there in LR? 204 is there, which will return into the program counter, so that you will come back to the instruction which is next to the call instruction. This type of supporting by two instructions called call and return, and establishing the linkage between the main program and a subroutine using a link register is called as a subroutine linkage. So people generally use a term called as subroutine linkage. So if somebody asks a question, how does the subroutine linkage is supported in the processor? It is supported by two instructions called as call and the return instruction, and by a link register. If you ask me the question, if I am calling another subroutine inside a subroutine, I'm making one more subroutine call, then how do you handle? Because there is only one link register there. Then it is a responsibility of the programmer to push the contents of link register into the process stack, and then you have to branch it. Some of the processor will support, that is why they support for the stack or subroutine nesting using called process stack. That means that whenever a call is there, automatically the return address is not saved in the link register. It will be saved in the process stack. The SP will automatically decrement whenever you call the instruction. Whenever you make another call from the subroutine, again the SP contents will be pushed onto the stack, and the return address is saved, and you can go to the another subroutine. Like that, when the subroutine nesting is required, the process stack and stack pointer are used to implement the nesting. So these are the concepts what is supported by the most of the process. So this completes the basics about the machine language instructions, how to write the program, assembler directories, the flags, the support for the input-output device, support for the stack, support for the subroutines. So if you have any questions, you can generally related to this, you can raise your question.